Hi guys, welcome back to my YouTube channel Study with Shakir. So today I'll be reviewing AP Statistics Unit 8. So a chi-squared. It measures the distance between observed and expected counts relative to expected counts. So a chi-squared statistic is given on the reference table. It's basically the sum of the observed minus expected squared over the expected. And expected counts are found by n, the sample size, times b, the statistics of the proportion. Or if we're given a table, it's the row total times the column total over the table total. Conditions that must be checked before a test is done, which is randomness, so a random sample like random assignment, independence, which is a 10% condition, and normal, that all expected counts are greater than or equal to 5. These conditions are needed for all the chi-squared. So a chi-squared distribution. To find this on the calculator, there is a chi-squared distribution, and the degrees of freedom needed is the number of categories minus 1. And as the degrees of freedom increases, it becomes more right-skewed, and a larger probability of getting a larger number. And the area under the curve is always 1, and it's only positive values, which makes sense because we're squaring it. And the median is the degrees of freedom minus 2, which is also the peak of the curve. Sorry, this is dirt, I meant curve. And the mean happens at DF. So an example, if the degrees of freedom was 4, the median is at 2, and the mean is at 4. So, how do we know which chi-square test to use? So, if there's 2 plus samples, it's a chi-square for homogeneity. But if it's one sample, it could be either goodness of fit or independence. So, if it's one sample and only one variable, it's a goodness of fit. If it's 2 plus variables, it's for independence. So, for example, homogeneity. So there's 2 plus groups. So the question would be like, do students from different schools have different favorite subjects? So there's multiple groups, like school A versus school B. And it doesn't matter if the categorical variable is 1 or 2 or whatever. Like favorite subject doesn't matter. We already know that for multiple populations. So we use chi-squared for homogeneity. Our goodness of fit. So the question would be like, do students prefer math, science, or English equally? There's one variable and one sample. It's from one specific school probably. And then one variable, which is just favorite subject. So we're using the chi-square test for goodness of fit. For independent, it's 2 variables and one sample. So it'd be something like, is there an association, which is a keyword, between gender and favorite subject? It's from one sample of students, so one population, one sample, and there's 2 variables, gender and favorite subject. So for this, we would use a chi-square test of independence. Chi-square test for homogeneity. It's used to compare distributions of categorical variable from multiple populations or multiple groups in a randomized experiment. So we would say HO, the null hypothesis, as there is no difference in distributions of blank among the groups, of course include context. And then the alternative hypothesis is that there is a difference in the distribution of blank among the groups with context, of course. For chi-squared for goodness of fit, it's used from one population and comparing one variable. So we would say for the null hypothesis is that the claimed distribution of blank is true. And for the alternative hypothesis, we say the claim distribution of blank is not true, in context, of course. Chi-square test for independence is used to determine whether the categorical variable are associated from one population and comparing 2 plus variable. So for the no, we would say that there is no association between blank for the whole population. And for the alternative hypothesis, we'll say there is an association between blank for the whole population. So chi-square test. So the p-value is assuming HO, the null hypothesis, is true. In context, the probability of getting a chi-squared, x-squared, of blank or greater purely by chance is the p-value. And it's usually always greater because we're squaring the values and we're just seeing what's above it. So the conclusions would be either if because our p-value is less than our a-value, we can reject HO. We have convincing evidence for HA in context. Or it could be because our p-value is greater than our a-value, we fail to reject the null, and we don't have convincing evidence for the alternative in context. So these are the steps for a chi-square test. We always define the parameter, the statistics, and the hypotheses. Then we always check conditions. And we state that what thing we're using. And then 4 is to calculate the expected values. 5 is calculate this chi-squared statistics. We always have to write the general formula and then the specific formula and plug in the values. And we can plug it into the calculator and find the values and find the extreme values just like in the calculator. And then we just interpret it if we're able to reject or fail to reject the no. So, for example, in the calculator, if we go to distributions, and we go to chi-squared. So, let's say that there are 4 categories. 4 minus 1 is 3. And then let's say we get a statistics of 0.6. So, we will see what's greater than. So, our p-value would be 0.89, which is definitely greater than our usual a-value of like 0.05. So, we fail to reject it. Or, you could always go to inference as well. we could go to test and then go to chi-squared. You could see if we're using goodness of fit or homogeneity or independence, doesn't matter, and you could just plug in the values and then keep going, and then it will give you the results. Now focusing on type 1 and type 2 errors. This table is specifically ingrained into my mind. So basically, on the top is it's true. True meaning that HO, the null hypothesis, is true. And false is basically saying that HO is not true and the alternative hypothesis is actually true. And then on the left we see rejected. That means we rejected the null. And on the bottom that we see it's not rejected by the null. So if we reject the null and we're right, the alternative hypothesis is actually true. It's the correct decision, the true positive, which is power. And the other correct decision is if HO, the null hypothesis, is actually true and we fail to reject it, it's also a correct decision. And it's a true negative. And we get this probability by doing 1 minus A. The probability of A is if we say that the null hypothesis is true, but we reject it. So it's an error. It's a type 1 error, a false positive, and that probability is A. And if we say that the null hypothesis is not true, we fail to reject it, but the alternative hypothesis is actually true, then it's a type 2 error, which is a false negative. And this is 1 minus power, which makes sense because each column adds up to 1. So it would be 1 minus the other, vice versa.
Like and subscribe and comment.